Welcome back. In this video, we are going to solve some exercises of chapter 0. I will not solve them all because many of the exercises are repetitions. So in principle, you encountered them in second and third year, but they are completely solved on my website. Okay, so here I'm going to just solve the exercises that we shall need later in later chapters. Okay, so let us start with exercise 8. So we have a normed space E, and we have an element F in the dual of E. We have to show that the norm of F, the operator norm of F, which is the supremum of the absolute value of X on the closed unit ball, we have to show that we can remove the absolute value, as I said in the lectures. And second thing, if we take the infimum of f of x on the closed unit ball or on the unit sphere, we get minus the opposite of the norm of f. Okay, so part A. First of all, f of x is always less or equal than the absolute value. The absolute value of f of x is either f of x or minus f of x, which is the same as f of minus x because f is linear. So on the one hand, when you take the supremum over the closed unit ball, we get the supremum of f of x is less than the supremum of the absolute value. So this is just one half of the equality. And now on the other hand, if you take an arbitrary element in the closed unit ball, then the absolute value of f of x is either f of x or minus f of x, which is the same as f of minus x. Okay? Now, since the closed unit ball is symmetric, so if x is in the closed unit ball, then the opposite, the symmetric, with respect to the origin, is also in the closed unit ball because they have the same norm, which is less or equal than 1. Okay, so in both cases, we have the absolute value is less than the supremum of f of x on the closed unit ball. So I take the supremum now. So this is an upper bound of the absolute value. Therefore, we get the reverse inequality, and therefore we have equality. And if you do the same thing with the unit sphere instead of the unit ball, we get the same relation. So we can drop the absolute value. Now, if we take the inf, we get minus the norm. Why this is true? So again, we use the symmetry of the closed unit ball or the unit sphere, same thing. Now we know that the inf of a subset of the real number or the real line is minus the sup of minus a, if you like. So get 2 minus, and this is easy to check. Okay, so if you like, double inequality, if you like. So the inf is minus sup of minus the quantity. Okay, this is the first remark. And now minus f of x is f of minus x. Okay, and by symmetry, the sup of f of minus x when x in the unit ball is the same as sup of minus x in the unit ball. So you can replace, if you like, minus x by y, and you get the sup of f of y in the closed unit ball. Same thing, by a change of variables, if you like. But the minus is outside. Okay, and we know that this is minus the norm by the previous result. Okay, and that's it. Now we can do the same reasoning. We can take the inf and the sup over the over the unit sphere, and we get the same thing. Okay, so we shall use this in chapter 3. Okay, so minus the norm of an element in the dual is the inf of f of x on the closed unit ball or on the unit sphere. Okay. Exercise 11. You probably encountered this exercise in second year. So what is the geometric meaning of these identities? lambda BAR is the homothetic of the ball of center A and radius R with respect to the origin. So when I do a homothency with the ratio lambda and center 0, the center, we have to take the image of the center under this homothency and multiply the radius by lambda. Second inequality, when I translate a ball, I just translate the center. And the sum of two balls is a ball, actually. This is, what's the meaning of this? This is the set, by definition, the sum of two sets, as we explained in the lectures, is the set of elements that can be written as the sum of two elements, the first one here, the second one here. Okay, so let us start with the first identity. Okay, we can do an equivalence. So what does it mean to take, take an element here. So x is in the homothetic of this ball. By definition, this means that x can be written as lambda times some element y here. So x over lambda belongs to this ball. This is by definition. This is equivalent to the multiplication of a set by a scalar. Okay? And now I go back to the definition of a ball. So this means that the distance between this element and the center is less than the radius. And now this is equivalent when I multiply by lambda, by absolute lambda, actually, because, yeah, lambda should be positive. Because otherwise we may have troubles, because if lambda is negative, we get a negative radius. So this is not true. Okay. If lambda is negative, we should take absolute value of lambda here. Okay, because this is just symmetry, by symmetry. But since lambda is positive, I multiply everything by lambda, and this is equivalent to saying that x minus lambda a is less than lambda r, and this is precisely, this happens if and only if x belongs to the ball of center lambda a and radius lambda r. So an element is here if and only if it's here. So we have equality. Okay, second identity, also we can reason by equivalence. So x is in this translate of the ball if x minus a belongs to the ball, and this happens if the distance between x minus a and b is less than r, but x minus a minus b is x minus the sum. Okay, so the distance from x to a plus b is less than r, so this means that x belongs to the ball of center a plus b and radius r. So this is very easy. Last identity, less trivial. So we split it into two inclusions. So first inclusion, this set is contained in this set. This is a consequence of the triangle inequality. How do I prove this inclusion? I take an element here. So it is the sum of an element here and an element here. So if you like, if you take z in the sum, so z equal to x plus y, x here, y here. So the distance between x and a less than r, the distance between y and b is less than s. So the distance of x plus y from a plus b is, if you use the triangle inequality, you'll get that x plus y minus a plus b is less than r plus s. So just apply the triangle inequality. So you write the details. It's easy. Now, conversely, you take an element in this ball and prove that it can be split into two as a sum, can be written as a sum of two elements, one here, one here. So we take an element x in this ball, and now I will give you the answer. So just take x1 to be a plus a scalar times x minus a minus b, so r over r plus s. And you take x2 to be b plus s over r plus s times the same thing. Okay, so now if you do the sum, why did we choose that? Because if you do the summation, x1 plus x2 is a plus b plus r plus s, r over r plus s plus s over r plus s. So this is 1. So it gives you a plus b plus x minus a minus b. So this is x. So x is the sum. And now it's easy to check that x1 is in this ball because x1 minus a is just r over r plus x s minus a minus b. So when you take the modulus, the norm, you'll get it's less than r over r plus s times r plus s. So this is r. So it's easy to check now that x1 is in the first ball and x2 is in the second ball. So an element here is here. And this concludes the reverse inclusion. So we have equality actually. And now, as you may observe that if we put less or equal here, we get less or equal here. So this means that the same identities work if we take closed balls instead of open balls. So I can write lambda b prime ar is b prime lambda a lambda r, a plus b prime is b prime, b prime, b prime, b prime. Okay, so exactly the same reasoning. Okay, so these are very useful relations in any norm space. Exercise 12, you probably encountered it in second year or third year, I don't know. We consider two subsets of a norm space, A and B. The first one is closed, the second one is compact. We have to show that the sum is closed. It's not necessarily compact because it may be unbounded, but the sum is necessarily closed. And this is not true if you remove one of the assumptions. So if A is just closed, the sum of two closed need not be closed, and we can give counterexamples. You will see that we need the assumption of compactness. Okay. Okay, how do I prove that a set is closed? There are several ways. We can prove that the complement is open. We can prove that it's equal to its closure. So this is what we are going to do. We have to prove that this set is equal to its closure. So I have to prove that the closure is contained in the set. So I take an element in the closure, and I want to prove that x is in A plus B. Okay, so this means that the closure of A plus B is A plus B. Now, what does it mean? There is a characterization of the closure of the set of adherent point of a set. They are characterized by the fact, in a metric space at least, an element in the closure is the limit of a sequence in the set. Okay, this is a famous result in metric topology. So there exists a sequence xn in A plus B that converges to x. Okay, this is not true in any topological space. It's true in metric spaces. So what does it mean that xn is in A plus B? This means that we can write xn as the sum of two elements for each n. Xn is the sum of an element in A and an element. So you get two sequences, a sequence in A and a sequence of B, in B. Now I use the compactness of B. Compactness of B means precisely sequential compactness. So there is a subsequence of Bn converging to some element in B, of course. So denote this subsequence by Bnk. Okay? So what do you have? Xn converges to x. So in particular, Xnk converges to x. So Xnk is convergent. So I can write Xnk equal Ank plus Bnk. Xna is convergent to x, Bnk is convergent to b, therefore Ank is convergent to the difference. So Ank, the sequence in A, converges to the x minus b, and this element I put it equal to A. So I define A to be x minus b. Okay, now since A is closed, the limit must be in A. And therefore I can write x equal A plus b, where small a is in capital A and b is in capital B. So x is really in capital A plus capital B. So the closure of A plus B is contained in A plus B, which is of course contained in its closure to have equality. So A plus B is closed. Okay, we shall need this result, this very simple result in chapter 3. Okay, exercise 13 also will be needed later. We have a normal space E and a subspace F of E with non-empty interior. Non-empty interior means it contains a ball. So we have to show that F is the whole space. what is the idea behind? So if you think of subspaces as being kind of planes in a space or lines in a plane, a line cannot contain a disk, okay, and a plane in three-dimensional space cannot contain a ball, okay. So this is the idea. So we'll prove that any element in E is necessarily in F. Okay, so take first an element in the small a in the interior of F. Okay, what does this mean? It means there is a ball, a whole ball around A, totally contained in F. And I can take this ball to be closed, as we observed. So there is a closed ball of center A and radius R totally contained in F. Okay, we said that we can take open ball, closed balls, same thing. Okay. Because if we took an open ball then of radius r center A, then the closed ball of center A and radius r over 2 will be contained in the open ball and therefore in F. So I can change the r if I like. Okay. This is not a big deal. Okay, and this is the idea. We have to prove that an element of E is inside this ball. Okay, but an element of E can be very far, can be near infinity, but by a homotopy, I can transform this point into a point inside this closed ball or at the boundary, if you like. Okay, this is the idea. So you can draw a picture if you like. So you have a ball here and the point outside the ball. By a homotopy, we can transform it to a point on the boundary. And these are the formulas. So take an element x in E and define y to be a plus this scalar times x minus a. What is the geometric significance, the geometric meaning of this formula? This is precisely the homotopy of center A and radius r over the distance between x and A. Okay, so this is y, and I can solve this equation. I can solve x in terms of y. If you solve it, just subtract a, multiply by norm of the difference over r, and then add a, and you get this relation. So this is a bijection actually, because this is a homotopy. And now this y actually belongs to the sphere of center A and radius r. Okay, because when you subtract a, you get this. Take the norm, x minus a over sum is 1, so you get r. Okay, so it's on the sphere, so it's on the closed ball actually. So therefore y is in F. And if you look now at the expression of y, what do you have? A is in F, and x minus a. Yeah, so sorry, I have to look at this. Excuse me. A is in F, y is in F, and a is in F. So y minus a is in F because F is a subspace. Okay, because stable under addition and subtraction. So this is an element of F. This is a multiple of an element in F. So it's again in F. When I add an element of F, I get again something in F. So X is in F. Okay, so that's it. So we have a double inclusion. So E is contained in F, and of course F is contained in E, so I have equality. Okay. Next exercise. We have a subspace capital F of a normal space E, and we have an element in the dual of E. We have to show that if F is bounded here because it means that because F takes real value. So if F is bounded from above or from below on the subspace F, then F vanishes. This is again a consequence of the stability of F under multiplication by a scalar. Okay. So suppose first that F is bounded from above. So what does this mean? It means that for every x in the space, cap in the subspace, it's less than a constant alpha. Then this is a number because f of x once again is a real number. Okay, this is the meaning that f is bounded from above. Okay, now since F is a subspace, then if X is in F and T is the real number, then Tx is in F as well because it's a subspace. So f of Tx should be less or equal than alpha. But since F is linear, I can put the scalar outside. So I get T f of X less or equal than alpha. And this is true for every T, every real number T, and every element X in the space. Okay. Yeah. Suppose that F does not vanish on F. So I reason by contradiction. What does it mean? It means that F does not vanish at least one point. Okay, X0 in F. So we may assume that the value at this point of F is positive, because if it was negative, then minus f of x0 will be positive, but minus f of x0 is f of minus x0. So instead of x0, take minus x0. Same, it doesn't change anything. Okay, because x0 and minus x0 are both in this space. Okay, so we have now an element x0 in the space capital F, the subspace, whose image under F is strictly positive. Okay, so I can divide by this number and take now an element, a number t, which is bigger than alpha over f of x0. Okay, then when I multiply by f of x0, because it's positive, I get Tf of x0 is bigger than alpha. Okay, but Tf of x0 is less or equal than alpha, and this is a contradiction. Okay, so this means that there's no element in F at which F does not vanish. So F vanishes identically on capital F. Okay, this is a very important result that we shall use later. Now, what if F is bounded from below? We can repeat the same reasoning, but we are not obliged to do so. We can deduce the other case from this case, because if F is bounded from below, so f of x is bigger than alpha, then minus f of x will be less than minus alpha. So minus f is bounded from above. And by the first case, minus f vanishes on the subspace, and therefore f vanishes on the subspace. Okay. So this concludes exercise 14. Exercise 15 is a very useful exercise in convexity. We have to prove that in a normed space, the closure and the interior of a convex set is also convex. First question. Second question, if we take an element in C, in the convex set C, and an element Y in the interior, then the straight line segment joining X to Y is contained in the interior. Here I'm taking the straight line segment without its endpoints, because I put T strictly between 0 and 1. So X and Y, recall that X and Y are the endpoints. So I'm saying here that the interior of the segment, straight line segment, is totally contained in the interior of C. Okay, so only X could be at the boundary, if you like. And third question, the closure of the convex set C is equal to the closure of the interior, if provided, of course, that the interior is not empty, because it may happen that the interior is empty, and therefore in this case this relation is wrong. If the interior is empty, then this is empty, but C may be not empty. Okay, and this relation actually is not true for an arbitrary subset of E. Okay, so we use convexity. Usually this is smaller than this, because the interior of C is contained in C. So and take the closure, it's contained in the closure. So you just have one inclusion. Okay, the reverse inclusion need not be true, and you can give counter examples if you like. Okay, so first question. How do I prove that C bar is convex? I go back to the definition. So I take two arbitrary points X and Y in the closure of C, and I pick any element T between 0 and 1, and I have to prove that the convex combination of X and Y, any convex combination of X and Y, is in C bar. Okay, so since X is in C bar, then by the characterization of the closure, there exists a sequence Xn in C converging to X, and similarly for Y, there exists a sequence Yn of C converging to Y. Now, I use the convexity of C. So this convex combination of Xn and Yn belongs to C because C is convex. Okay? Now, since xn converges to x and yn converges to y, this convex combination converges to 1 minus tx plus ty. This is the continuity of the elementary operations. Okay. So if xn converges to x, any multiple of xn converges to the multiple of the limit. Okay, and same thing for sum. So the limit must be where? In the closure. Okay. So that's it. This is very easy. So any convex combination of x and y is in C bar. So C bar is convex. Okay, so this is pretty straightforward. For the interior, a little bit less trivial. So, but the same methodology. So we take two elements x and y in the interior of C, and we pick an element t strictly between 0 and 1. Of course, it's enough to take t strictly between 0 and 1, because if t equals 0, then we get just x, the one endpoint. And if t equals 1, we get the other endpoint. So, and there's nothing to prove here. So, okay. Now, since x is in the interior of C, then by definition of the interior of a set, which is the biggest open set contained in C. So if x is in the interior, then there exists a ball around x totally contained in C. Okay, this is by definition of an open set. Okay, and similarly, if there is an open ball of center y. Now I can take the same radius y, because if here I have a radius r1 and here a radius r2, I take the minimum between the two. So I can take the same radius if you like, by shrinking the ball if possible, if necessary. Okay, and now, therefore, when I multiply by 1 minus t, so the homothetic of this ball with the ratio 1 minus t is contained in 1 minus tc. And similarly for the other one. So TBYR contained in TC. So the sum is contained in this sum. So this is just set theory. But now, here I use the convexity of C. 1 minus TC plus TC is not necessarily contained in C. It's contained in C if C is convex. Okay? So this linear combination of balls is contained in C. Right? And now, I used a previous exercise 11, that tells me that this first set is the ball of center 1 minus tx and radius 1 minus tr, and this ball is, so tbayr is the ball of center ty and radius tr, and the sum of these two balls is the ball with the sum of the centers and sum of the radii. So 1 minus tr plus tr is just r. Okay, so I got that the ball of center, this convex combination, and radius r is contained in C. So this precisely means that this center is in C, is in the interior. Okay, and that's it. Okay, last identity. So we just have to prove one implication. Okay, so we have to take an element in C bar and prove that it's here. Okay, first of all, you have to notice that sorry, what else? Sorry, excuse me. Sorry, this is question B. Excuse me. So we have x in C and y is in the interior. We have to show that the interior of the straight line segment is in the interior of C. Okay. So since y is in the interior of C, then there is a whole ball of center y contained in C, as you observed. And since C is convex, so 1 minus tx plus tbyr is contained in C. Okay? Because this is a convex combination of x and any element in the ball. Okay, by convexity, this set is contained in C. Because you take any element here, then it's here, because C is convex. And now, if you reason as in exercise 11, this is actually what? This is a translate of a homothetic of the ball. So we can just, okay, first of all, I can put the t inside. So I get bty tr. And then when I add the center, so I translate the center, I get the ball of center 1 minus tx plus ty tr. Okay, so this is by exercise 11. Okay, so here actually so I found a whole ball around this element totally contained in C. And this means that the center is in the interior of C. Okay, last question. So as you observed, one inclusion is clear. The reverse inclusion, you take an element x in C, and we fix an element y0 in the interior. Okay, according to question B, I take t equal 1 over n. So this convex combination of x and y0 is totally contained in the interior, right? For every n. When n tends to infinity, this converges to x. So x should be where? The limit should be in, it's not necessarily in the interior, but it's necessarily in the closure. So x is in the closure of the interior. Okay? So C is contained in this. But by definition of the closure of a set, this is closed. This is a closed set containing C. But C bar is the smallest closed set containing C. So C bar is contained in that bigger set. And therefore we have equality. So this is by definition of the closure. Okay, exercise 16. We consider a function between two metric spaces, and we consider the graph of the function. The graph of the function is a subset of the product x times y. Okay, the graph of a function is by definition the set of couples of the form x f of x, where x is in the source space. Okay, this is what you draw when you draw the graph of a function. Okay, first question, if f is continuous, then the graph is closed. Of course, here we consider x times y with the product topology. Second question, the converse is not true, but it's true if the target space is compact. Okay, so we shall go back to this in chapter 3. Okay, first question is easy. Why the graph is closed? How do I prove that a set is closed? I take an element in the closure. So by the characterization of the closure, I can find a sequence x and y n in the graph that converges to this point xy. Now by definition, so this if x n y n converges to xy, it means that the first component converges to the first component because projections are continuous, and second component converges to second component. Okay, this is by definition of the product topology. Now, if x n y n is in the graph, then necessarily y n is the image of x n under f. So what do we have now? X n converges to x and y n converges to y. But since f is continuous, it is sequentially continuous. So f of x n converges to f of x. But in a metric space, limits are unique because a metric space is a Hausdorff space. So you get y equal f of x. And this precisely means that xy is in the graph. So I took an element in the closure of the graph and proved that it's in the graph. Therefore, the graph is closed. So this is straightforward. Now we can generalize this, but we have to assume that y is Hausdorff actually, because in order to obtain uniqueness. So we can generalize this to a more general context, but it's easier to work with sequences. Okay, so I simplified a little bit the exercise by assuming that everything is metrizable. Okay, the converse is not true. Here's an example. I take the hyperbola 1 over x, but I define it to be 0 at 0. Now I can define it to be anything. Not 0 is not something important. You can put 1, you can put 2, any number, okay, but not infinity. And now, so the graph of f is actually consists of 3 pieces. A branch of a hyperbola, another branch, the symmetric, and 0. Now, it's easy to prove that each branch of the hyperbola is a closed set in R2. It's very easy. You can, how do you prove that? You take an element in the closure and prove that it belongs to the set. So, same argument. So, the upper branch of the hyperbola is a closed set. Of course, the image of 0 is the singleton 0 is closed, and the other branch is also closed. So, the graph of this function is closed, but f is clearly not continuous, no matter how I define it at 0. Okay, so the converse is not true. If the graph of a function is closed, it doesn't mean in general that the function is continuous. Now, I will present a case where the converse is true, and you shall see another situation in chapter 3 where this is also true. Okay. So now I suppose that y is compact, first assumption, and the graph of f is closed. I have to prove that f is continuous. So it's enough to prove that f is sequentially continuous because they are equivalent in the context of a metric space. So I take a sequence, an arbitrary sequence, xn converges to some limit. Okay, and I have to prove that f of xn converges to f of x. Okay, now f of xn is a sequence in y, but y is compact. So sequential compactness implies that there is a subsequence of f of xn, which can be denoted by f of xnk, that converges to y. And now the sequence x and k and its image under f is in the graph, by definition of the graph. The first component converges to x because it's a subsequence of xn. If the whole sequence converges, any subsequence converges, and f of x and k, f of the subsequence converges to y. So this sequence in the graph converges to xy. But we assume that the graph is closed. So necessarily xy is in the graph. The limit is in the graph. So necessarily the second component is the image of the first component. So y equal to f of x. Okay. So I have f of x and k converges to f of x. Okay. And by a result in the lectures, this implies that, actually I didn't prove that directly that f of xn converges to f of x, but I proved something a little bit weaker, but it's actually equivalent. Because if you recall a proposition in section 1.2, 0.2, if for every sequence xn converging to x, there exists a subsequence of xn whose image converges to f of x, then f is continuous at x. Okay, because I gave 6 equivalent conditions equivalent to continuity. So actually, we can prove that f of xn converges to f of x. Okay, but you don't know that in this. Okay, so f is continuous at x. Since x is arbitrary, f is continuous everywhere. So here we used an extra assumption about compactness of y. Okay. So this argument does not hold if you don't assume compactness. Okay, last exercise. It's related to Ritz theorem about the non-compactness of the unit sphere or the closed unit ball in an infinite dimensional space. Okay, but first a preliminary question. In a norm space, all open balls are homeomorphic and all closed balls are homeomorphic. Okay, here we are taking the norm topology or the strong topology. Okay, this is easy. So it's enough to prove that any ball, any open ball of center A and radius R, is homeomorphic to the standard, to the open unit ball of center 0 and radius 1. Okay, but by exercise 11, this ball is the image of the standard ball by a homotopy followed by a translation. Okay, can do a picture. Take any ball. If you translate it, you get a ball around 0, and then you dilate the radius, and you get, or you shrink the radius, you get the standard ball. So any ball, the ball of center A and radius R is the image under this map, which is a homotopy followed by a translation. And this is, of course, continuous because of the continuity of the fundamental, okay? Homotopy is continuous, translation is continuous. And therefore, the ball of center A and radius R is the image under a continuous map, under a homomorphism, actually, because, and here it's important to assume that the R is positive, because if R is 0, actually, this is just the center and it's not open. So the convention is that whenever we consider radii of balls, they are strictly positive. So this phi is actually a homomorphism, okay? Because we can find the inverse. Actually, the inverse of phi is, so phi minus 1 of y is y minus a over r. Okay, so this ball is homomorphic to the standard ball, standard open ball. And I can do the same thing with closed balls. So if I put here B prime, then I get B prime here. Okay, so all open balls are homomorphic to the standard open ball, and therefore they are all homomorphic between each other, because homomorphisms is an equivalence relation, and same thing for closed balls. Okay, now second question. A compact subset of an infinite dimension norm space has empty interior. This is a phenomenon which is which characterizes infinite dimension spaces. Okay. Reason by contradiction. If the interior of a compact set is not empty, then by definition it contains an open ball and also a closed ball as well. Okay, so it contains a ball, a closed ball of, let us say, the center A in K and some positive radius R. Okay, so what do we have? This is a closed set which lives in the interior of K, and so in K. So this is a closed subset of a compact space. But closed in a compact is compact. So this closed ball is compact. By homomorphism, the closed unit ball is compact, according to the previous question. But if the closed unit ball is compact, then the space is finite dimensional. So we get the contradiction. Okay, so this concludes this video, and we are done with chapter 0, okay, which was a foundation. So if you noticed, many things were a review, but this is really a foundational chapter for the course. So it's not a waste of time to review all these notions and details about norm spaces, topological spaces, vector spaces, and so on. Okay, so thank you for your attention and see you next time.